Hello, my name is John Gabriel, and this is the New Calculus channel. Today, I'm going to talk to you about a very special feature of the New Calculus, one that you meet almost right away when you begin to study the New Calculus derivative. And this is long even before you get to the New Calculus integral. So there are many features, but none as important and with the scope of application of the auxiliary equation. I'm not able to cover all its uses and all the facts about it in just this one lesson. But I'm going to try to explain it to you so that if you have a high school math education and you're able to do algebra, trigonometry, and geometry, then you should be able to understand this because there's nothing really complicated about it. And of course, if you're somebody like Dennis Miller or James Meyer or that idiot lecturer from France, Jean-Pierre Messager, or perhaps Jan Bursa from Switzerland, troll on Sci.Math, and last but not least, that incredible moron Dan Christensen from Canada who also lives on Sci.Math. So unless you're one of those, or perhaps Professor Gilbert Strang from MIT or Professor Jack Hazinga from Harvard, they're all idiots. And what you're about to see is a very simple, systematic explanation of the auxiliary equation in the New Calculus. So let's begin. Now, the New Calculus derivative is stated as follows: f prime of x, and by the way, that's just a notation that you see there, okay? Newton, for example, used different notation. It's stated as f of x plus n minus f of x minus m over m plus n, where m and n are horizontal distances from the point of tangency x fx, see? Horizontal distances to the endpoints of a secant line, a parallel secant line, this blue parallel secant line. And what is it parallel to? The red tangent line. Wow, that's really easy, isn't it? Okay, so that is the definition of the New Calculus derivative. And it works for all calculus in one dimension and multi-variable calculus and partial differential equations and everything else. Let's proceed. The New Calculus derivative can also be written as what you see there, where q of xmn is a function or an expression containing any combination of x, m, and n, and it's always equal to 0, as you see over here. This was proved in the video that I showed you up here, in this video here, okay? So I think I skipped this slide on my way down, but you might recall how I explained how all this works in the video found at this link. And I showed you how this auxiliary equation is derived, and I only called it auxiliary because it has so many uses that it was hard to actually state, you know, a more specific name. So auxiliary means a helping or assisting equation, okay? So the New Calculus derivative is written also like that, where this is actually equal to 0. And because of this particular format, we're actually able to find this expression using this equation. Let's see how. We're going to use the example of the cubic, and there's nothing special about it. You can use any function you like. Each and every function that is continuous and smooth, and it's not necessary to mention continuous, only smooth, there is an auxiliary equation. So provided the function is smooth or differentiable, as you hear in mainstream circles, over a given interval, then you will be able to find an auxiliary equation. Actually, it doesn't, the interval has nothing to do with it, but there are other specifics that come into play, which we'll see in a moment. So frankly, it does not matter because it works for any function, but I'm using the cubic because that's simple for you to understand. It'll work with sine x, cos x, logarithm of x, anything you like, okay? Now, so what we do is we start off with a definition and we expand that using the binomial theorem, do the simplification, and we end up with this. This here is the derivative, by the way. Yeah, that's right, because this part over here is the expression which is always equal to 0. It's called the auxiliary equation when we add equals to 0 at the end. But the 3x squared is not included because that's f prime of x, okay? And again, as I said, I proved all that to you in this video. All right. So one thing to note is that m plus n, this m plus n, is always a factor of every term in the numerator. And there is always one term that does not contain either m or n, and that term is the gradient, f of x. Okay, in other words, it's a term only in x. Now, that term also has a factor of m plus n, otherwise you'd see it down here in the final state. So this has been proved for all functions. Now, if you think otherwise, and you'd like to argue otherwise, like one of the morons on sci.math or any of the other websites by the cranks that are out there, try to find a counterexample. And I'll tell you what, I'll come out and I'll openly admit that I'm an idiot. How's that? Good luck. That's all I have to tell you. I left out the working because any high school math student will know how to go from this step here to this step here, okay? So you can actually just simplify this expression on the right to get that. And then this expression here is the auxiliary equation when you add equals 0. In this part here is just an expression, but add equals 0 will make it an equation. So I'm trying to be slow so I can fit in everything correctly for all the people that are not so intelligent out there. And trust me, there are many. So we know that this equation here is true, don't we? Okay. We know that it's true. So if this is true, then we also know that f prime of x is equal to 3x squared. So we have this equation, and these cancel out, and we end up with the auxiliary equation, which is what you see down here, right? Okay? And we can move from this step to the next, which is we can solve any one of x, m, or n given the other two. This is always the case in the new calculus. And with simple curves, you don't even need iterative methods like, Newton's root approximation or anything like that. And there is no need to learn the bogus theory of limits or to entertain ill-formed concepts such as infinity or infinitesimals. The new calculus treats all variables as distances, not actual numbers, because not all distances have numbers that describe them. So for example, when you work with pi in an equation, you're just using the symbol pi. It's not a number, it's just a symbol for the distance or the magnitude that we've come to realize as pi. Okay, it has no measure. That's why the ancient Greeks called it an incommensurable magnitude, because a magnitude is not a distance, is not a number. A magnitude is a distance, but a magnitude is not a number, and a number is the measure of a magnitude. Think about that. Pause your video right here before you continue. So, the new calculus treats most variables that you see, which are not numbers, as distances, because you can't really be sure that they're numbers unless you can measure them. Now, the auxiliary equation applies to every point in a given smooth interval. So for example, if you had an absolute value function like that, calculus is not even applicable at the point 0, because it's not smooth at the point 0. In fact, A straight line doesn't have a derivative. It has a slope, but not a derivative. There's a very subtle distinction there. And I've discussed all of that in other videos, so I'm not going over it here again. Now, the equation applies everywhere except a point of inflection. Only in your bogus mainstream calculus is it possible to have a derivative at a point of inflection. In fact, if the only mn pair that satisfies this here is 0, 0, then you can know that that is a point of inflection. But in your bogus calculus, what happens? Let's see. In your bogus calculus, you have several problems. First of all, a tangent line does not always imply a derivative and vice versa. But in the new calculus, it does. So it's consistent, unlike the mainstream calculus. If the only mn pairs that satisfy the auxiliary equation is 0, 0, then you can know that there is a point of inflection at the given x. It's as simple as this. There's no first or second derivative tests, and nothing left to chance or stupidity, the which there is very much in mainstream academia. Now, to draw a parallel secant line in a graphics program using your bogus calculus, you need to perform intensive iterative algebra with special algorithms, and I mentioned one, Newton's root algorithm, or something like the Durand-Kerner, etc. I don't really care which iterative method you use, but there are many. Not so with the auxiliary equation in the new calculus. Let's continue with our example. So from the auxiliary equation, this equation down here, we can find m in terms of x and n. That is mxn. Okay, or we can find n in terms of x and m, and that is nxm, as you see here with two inputs, x and m. And so we take that equation and we rearrange the terms a bit, and we notice that we have a quadratic in m, right? And therefore we can solve it, and we have the first equation. Don't worry about the plus and minus here, I'll explain it in a moment. Similarly, for n of x and m, we have another equation as you see here. And now, those are the two auxiliary equations here at the top. And of course, the sign of this radical here is easily chosen by observing the tangent space. Okay, and I'll tell you what the tangent space is not right now. It's related to this triangle here that you see when you draw a parallel secant line. It's a similar triangle, and it has two similar triangles, but it's related to that. And why did I do that? I didn't mean to do that. Oops. Close that. So let's go back to the document. Now, so if, for example, you're looking at the auxiliary equation for m, this sign here is usually a minus because it lies to the left. In other words, m is the distance to the left of x, and n is the distance to the right of x. So that's how you determine which sign to use. So this is, down here are the final two equations, as you see them stated here, minus and plus. Now let's see how this works in practice. So let's come over here. So this curve here is just the equation of the cubic, y is equal to x cubed. And these are the two equations that you saw in the slide. And I can show you right now that it doesn't matter where you are with a parallel secant line or which point of tangency you have. These distances here that you see will basically be related to each other and to the point of tangency by these equations. So now, for example, if we wanted to find m, as you see here from n, we would put the distance n inside here, and it will be the distance n inside here, and it will be calculated using this equation. So if you put n in here, let's say you put this value up here, which is 27414. Let's do that, 27414. Then once we press enter, this value here should be this red value that we have up here, right? So let's see, does that work? Yes, as expected. Similarly, using this equation here, you can find n from m. So if you decide to put in a value of m, this value of m, which is, let's say, 21454, then this value down here should become the blue value once we hit enter. As expected, it does. And so the new calculus is not a joke like your bogus calculus. It's very sound. It's carefully engineered, thought out, systematically, using well-formed concepts. Before I came along, nobody knew what a well-formed concept is. In fact, they didn't even have methods or rules to determine what it means. And I encourage you to go to my website, to my article rather, not my website, but you should also visit my website. And there you will see an article called, let me just get rid of that. It'll be called, "What does it mean to define well-formed concepts?" I strongly encourage you to read that article, okay? Okay, it's a little bit slow because I'm actually recording, so let's just leave that for the time being. All right, so I don't think there's anything else I need to add, but I mean, this value here obviously will change n from n as I move along here. And this value gets calculated on this n, not on this n. And similarly, this one on this n. This one on this m and not on this n. I'll upload this applet, and I'll also upload this document so that you can actually read it and play around with it. Now imagine that you try to do any of this with your bogus mainstream formulation of calculus. You would hit a snag right away because an auxiliary equation is not possible in mainstream calculus. So what you'd have in mainstream calculus is something like this. Well, we know that qx of h must be 0, right? Because under no circumstances can we have that where h is equal to 0. Or in fact, even without, we can't have that because this finite difference quotient is not the same as the limit, see? So you would be able to find some expression if you do it this way, but this is not true. This here is not true because this particular expression here must be equal to the derivative. So with respect to the previous example of the cubic, we would have this expression down here if we followed this general idea and we said, okay, let's just try it anyway. Let's ignore the flaws and try. And anyone knows that f prime of x is not equal to that because h cannot be 0, right? So in your bogus calculus, qx of 0 is required to arrive at the derivative, but h equals to 0 is not allowed. So basically, you're dangling around the point of tangency, not knowing what on earth you're doing. And of course, for good reasons, h is not allowed to be equal to 0. But you're basically screwed whatever you do in your basic calculus, in your mainstream calculus, which is flawed and a bogus formulation. But even if we let these flaws slide and try to continue, there's immediately a problem. Okay, and so we see the problem here. What we need is to solve this particular equation here, this last bit, and we'll see there are only two values of h that will make the equation true. That is, h is equal to minus 3x, which, by the way, doesn't make any sense because it's absurd. And h is equal to 0, which is not allowed. So it's definitely a euphemism for me to say that your mainstream calculus formulation is a bunch of crap. Now, comparing the flawed mainstream calculus to the new calculus is similar to comparing Stonehenge with the Parthenon marbles, also commonly known as the stolen Elgin marbles. The new calculus is the greatest discovery of human ingenuity, and you haven't even studied the new calculus integral definition yet. And there are many things about the auxiliary equation that I haven't told you about. And there are many theorems I haven't even yet discussed with you, which are not possible using the machinery, the broken machinery of your Stonehenge calculus. Did you get that? I love rubbing it in. So I hope you've enjoyed this presentation. I've tried to be civil. Remember, when I do become abusive, it's not towards those that have an open, astute, and intelligent, receptive mind. It's directed, my hatred is directed at the Gilbert Strangs of MIT, the Jack Hazingers, the David Joyces, the David Ulriches, all those morons who have crossed my path in the past, the Anders K. Sorgs. They're not directed at you if you have the right attitude. So in future, have a good laugh when you hear me abusing those morons. I'll tell you what, I hate them with such a hatred that it can't be described in words. They're jealous, they're evil, they're perverted. They cannot realize well-formed concepts. Everything they do is ugly, like they are ugly, and like George Cantor was ugly with his theory. And what I'm showing you now is the light and beauty of the new calculus and mathematics. And I have much more to say, and if the future and other factors permit, I'll continue to make these videos. So I hope you've enjoyed this presentation. My name is John Gabriel, and this is the New Calculus channel. Till next time, goodbye.